Swayam Prabha. Digital India. Educated India.
So, in the previous lecture, we introduced this class of strategies called mixed strategies. And these were a generalization of our earlier strategies. The earlier strategies were then called pure strategies. So, a mixed strategy, remember, was a mixed strategy is a probability distribution on the set of pure strategies. Now, we were talking in the context of a zero-sum game. So, if you recall, then if for the row player, then we had a zero-sum game A, which denoted a zero-sum game. And then for the row player, mixed strategies for the row player, this was a set of capital Y, which comprises of all vectors y in now that have m rows. So, column vector of length m such that every component is greater than or equal to 0, and if you sum over all the components, you get 1. And similarly, so this was for the row player. And similarly, for the column player, you had a set Z, which was all the Z's in Rn, which is the number of columns, such that Z is greater than or equal to 0, and the sum of the Zj's is equal to 1. So, these are the mixed strategies for the column player. Okay. And then we said let's define similarly security strategies and security levels. So, the security strategy for the row player, it was a y star in y, such that y star transpose A z is less, the maximum of y star transpose A z is less than or equal to the maximum of y transpose A z for all y in capital Y. And similarly, for the column player, it is a strategy Z star such that the minimum over y in y of y transpose A Z star is greater than or equal to the minimum over y in y transpose A z for all z in capital Z. Okay, all right. So now, assuming that these security strategies exist, these were called the security levels, the mixed security levels. So this is what we called VM upper bar, VM upper bar of A, and this is what we call VM lower bar of A. And now, assuming such the security strategies and security levels exist, we got that we derived last time this series of inequalities. Now, one thing which is actually quite straightforward here is that the mixed security levels actually exist, provided I be a little more careful with my with my notation here. All I need to do is I replace the max here by a sup and replace the min here by an inf, then the mixed securities levels will exist. But what I will show today is that actually the max, the way they are defined here, they also, the mixed security levels in this way also exist. Okay. So first let's just consider what exactly is the issue. I mean, why do we need to look at this carefully? Why is it not automatic that a security level exists? Okay. So if you see what we are doing here, the y star basically is the y that minimizes this expression. It minimizes the max over z of y transpose az, right? So y star solves basically the minimum over y, minimization of over y of the maximization over z of y transpose az. Now, if you look at this thing here, this is now a function of y. Now, question really is when does a function of y like this, okay, have a minimum over a set capital Y. Capital Y is an infinite set, so it's possible that this function doesn't attain its minimum over this particular set. Okay, I'll give you an example. For instance, look at this. Suppose this function of y here was like this. Okay, this is y. The function of y behaves this way. It reduces up until this point. Let's say some point here, some point y bar, and then out here at this point it jumps and then increases this way. So the value at y bar is actually this, the dotted value here. Okay. So the function decreases till y bar, but at y bar the value is not this point, but rather this point. Okay. In that case, question is, does the minimum of this function does this function have a minimum? Oh, and suppose you want to minimize this function over this set y, and let's say y is this, this set here is y, is capital Y. So does this function have a minimum over capital Y? The function doesn't have a minimum over capital Y, but it has an infimum over capital Y, right? So there is a least value for this function, and that least value is this, but that least value is not attained in the set capital Y. Okay, so there is no point in the set capital Y whose function value is exactly equal to the yellow value I have marked here. Okay, so this is a case where minimum is not attained, or infimum is not attained. What are the other reasons for which? Can you imagine other situations where where you may not get a minimum in the set? What other situations could arise? Sorry? Okay. So, alright. So, I'm not sure which exact case you are referring to, but here is one possible case. Another case where the infimum is there is finite, but it is not attained. So, here is for example another case. So, suppose I take the set Y as an open set. So, I include, so my Y now, capital Y, is from this point till this point. Okay. So, let's suppose this is small a and this is small b. Okay. So, if I consider Y to be an open set, okay, then you have the set Y. So, suppose Y is an open set where it is an interval from small a to small b. So, this being an open set means that small a and small b are not included. And now, suppose the function that I am minimizing is just this. In this case, what is the least value of, what is the infimum of this function over this set? The infimum of this function is this. But is there a point that attains that particular value in this set? No. If b was in the set, then it would have been, but b is not in the set. Okay. So, again here, so in this case the culprit for non-existence of or non-attainment of the infimum is actually that the set is a problem. Okay. Whereas here in the earlier example, the reason for the non-attainment was that the function had a jump in it. Okay, the function was broken, whereas here the problem is that the set is open. Okay. What about, there is also a third case. Let me draw that third case also here. So, this is what I am attempting to draw here is a set Y which is let us say from 0 all the way till infinity, and this function that keeps decreasing and eventually say let us say settles finally at some value like this. This is the value that it finally settles at. Okay. But what do you mean by settles at? That is the limiting value of this function. So, as y goes to infinity, that is the value of this function. So, now is there a y as a real number that attains this particular value? There isn't. So, it's a classic example of this would be say a function which say take e to the minus x. Okay, take the function e to the minus y, and y in capital Y, which is 0 to infinity. Now, what is the infimum of this function over capital Y? It is 0. But is there a y that gives you e to the minus y equal to 0? There is no real y like that, right? So, the only way you can get 0 is actually if you put y equal to infinity, but that is that is effective, that is not a real number. Okay. So, the way, so another culprit for non-existence, non-attainment for the infimum in the set is that the set sort of runs away. As you keep, the function value keeps decreasing and you have to go further and further and further, and to find a lower and lower value, but this process becomes endless and you eventually never get to the least value. So, the point is it turns out that these are the only 3 possibilities. So, if you can plug these 3 possibilities, then there will always be a function will always will attain its minimum over a set. Okay. So, these 3, so there is a theorem that basically comprises of this, that basically tells you this, and this is the sort of starting point of essentially any theory in optimization, and theorem is due to Weierstrass. Let X be a subset of Rn. Okay. and let f from x to r be continuous. If x is closed and bounded, then f attains its infimum over x. So, consider a function f and consider a set x in which is a subset of Rn, and let f be a function from x to r, and f is assumed to be continuous. Now, if x is closed and bounded, then f must attain its infimum over x, means that there must be a point in x. Okay. So, that means what this means is there exists an x star which is in x such that f of x star is equal to the infimum over x, x in x of f of x. Okay. So, what this is basically what this is telling you is that there is that whatever is the infimum value, this infimum value firstly is finite and it is being attained by some point in the set itself. Okay. All right. So, all we need to do now for claiming that so since we said that y star basically solves this problem, all we have to argue is that y star actually belongs to capital Y, because essentially this is, we want to say that if y, then it would mean that there is actually a minimum to this particular problem. Okay. So, in short, we want to argue that if you look at this function here, this function when minimized over y in capital Y gives you a y, is its minimum value is attained by a y star in capital Y. Okay. So, for okay. So, means there is a y star, that is there is a y star in capital Y such that if I take the max over z in capital Z of y star transpose A z, that is equal to Is this clear? Okay. So, in order to do this, what I need to basically argue is that this function here. So, the function that I am looking to that I am talking about now, the function is a function of y, and that is just this function, that is the max over y transpose A z. Okay, max over z of y transpose A z. All right. Now, this, if you remember, what did we see last time about, what did we say last time about this function? We wrote this out. We said maximum, if you look at the maximum over A z of y transpose A z, what was this actually equal to? This was the maximum over j of y transpose A j, right. So why was that? Because Y transpose A was a column vector, Z is a set of capital Z is the set of probability distributions, and therefore the maximum is going to be attained at when you put J is going to be attained at the by a probability distribution that puts full mass on the largest component. So this was actually equal to, so max over Z in capital Z of Y transpose AZ was basically was equal to the largest component of the vector Y transpose A. Okay. So now let's go back and look at this boxed expression here. So the boxed expression then is actually is in fact equal to the max over J of Y transpose AJ. Alright. So now what are these actually? What exactly have we written out here? This is basically, this here is a collection of linear functions. Okay, how many linear functions are these? There are they are indexed by J. So there is one for every J. So there are n linear functions, and you are taking the maximum of those linear functions. Each of these is actually a linear function. So linear function, each of these is a linear function of Y, and you take what we are what's written out here is the maximum of n linear functions. And so that is actually just the maximum of finite. So now if you take, so each of these linear functions, is it a continuous function of Y? It is, because it's after all just a linear function of Y, right? It's actually a polynomial in Y. So it's a continuous function of Y, and what you are doing is taking the maximum of finitely many of them. So if you take the maximum of finitely many continuous functions, what you get is a continuous function. Okay. So therefore this is a continuous function of Y. So therefore this is a continuous function of Y. Okay. So the boxed expression is a continuous function of Y. Now what about, so you are looking for the infimum of a continuous function now. Alright. Now are you looking for an infimum of a continuous function over now a closed and bounded set? Over what kind of a set? We are looking for, we are minimizing this over a set capital Y. What kind of a set is capital Y? So the capital Y is a probability distribution, is the set of all probability distribution. So naturally it is a bounded set because every component is between 0 and 1, alright, and it is also closed because if you take the limit of probability distributions, it is also a probability distribution. So capital Y is closed and bounded, and the boxed function is continuous. So what this means is you can directly apply Weierstrass theorem now. Weierstrass theorem is basically asking you to check two things. It's asking for, if it's saying that if your function is continuous and you are minimizing it over a closed and bounded set, then then its minimum is attained. Okay. So the boxed function is continuous. That's what we just argued. You're minimizing it over a closed and bounded set capital Y. So there is going to be a Y star such that that Y star attains this infimum. Okay. So in short, from this basically tells us from Weierstrass theorem. So from Weierstrass theorem, we have that there exists a security strategy I just argued for the row player, but similarly one can argue for the column player also. So there exists a security strategy for each player. All right. So in short, we are clean. We don't, security strategies as we just defined actually through the in fact exist. All right. So we therefore so this the inequality that I just wrote out, this whole inequality now is now proper. This chain of inequalities is now proper. Okay, that V upper bar is greater than equal to Vm upper bar, which is greater than equal to Vm lower bar, which is greater than equal to V lower bar. This is fine. Okay, all right. So now we come to the we can again, now that security strategies exist and so on, we can again talk of a saddle point, define a saddle point. So, a saddle point in mixed strategies is a pair y star comma z star such that, so this is the analogous set of inequalities holds. So, y star transpose az is less than equal to y star transpose az star, and y star transpose az star is in turn less than equal to y transpose az star, which means that, so a saddle point is a pair of strategies such that if the column player is playing z star, the row player would want to respond with y star, and if the row player is playing y star, the column player would want to respond with z star. Okay, so we have now defined a saddle point in mixed strategies, and as before, we again have that there exists a saddle point y star z star if and only if Vm upper bar is equal to Vm lower bar. The proof follows exactly the way we did for pure strategies. Okay, so we just defined a saddle point, and we said that, well, the saddle point exists if and only if Vm upper bar is equal to Vm lower bar. Moreover, we will also have all the other properties. If Vm upper bar is equal to Vm lower bar, then saddle points will be comprised of security strategies and so on. All of that, and every pair of security strategies is a saddle point. All of that will also hold. Okay, but remember, we have not yet. So this all we are saying is that there exists a saddle point if and only if this holds. Okay, we just defined what a saddle point should be, and we said that we can find a saddle point if and only if this equation holds. Okay, so the crux of the matter now is that we have basically come to exactly the same juncture that we had earlier, except that we now are in a different space. Earlier we were talking of pure strategies, we are now talking of mixed strategies. We have security levels again defined in terms of security levels and security strategies, all defined in terms of mixed strategies. Okay, so earlier what we found was there are games. Okay, there are matrices A for which V upper bar is not equal to V lower. Okay, and we extended the space to mixed strategies, and then we got this chain of inequalities. Now what I will show today is that this in fact is an equality.